So like I just finished saying here, when it comes to working with formulas in physics, this is kind of one of the main things we do. It's not the only thing we do, but being able to do some math calculations is important. And over here on the board in blue, I've written out what I consider to be the 4 main steps that I try to teach my students in physics, whether it's you guys in Science 10, whether it's my Physics 20 or 30 students. These are kind of the 4 steps. Can you guys see them in blue over there? So I'll just read them out here before we start our lesson. Number 1, usually step 1 is if you recognize, hey, it's a math type problem, identify, or what we're going to learn about today is you may have to build yourself your own formula. Okay, that's step 1. Yay. Step 2, the step that I think really differentiates students based on how much they love their math, use algebra to manipulate formulas. Okay, we'll work on that today. Step 3 is usually not as bad, substitute variables. So once you have a formula that's been rearranged through to algebra, most students at that point, if they did that right, are able to type numbers into a formula. And then the last step, which hopefully I've done a good job of helping you with over the last couple of weeks, do you know how to add the proper units and round with significant digits? So that's our goal for the day. Before we get there, though, we need to talk about a theory or a concept. Okay? Whenever I teach, regardless of my physics level, but it usually goes like this. First, we teach a physics principle or concept. And then after the concept, then we do the math. So let's do the concept first. In science, there's what we call 3 different types of systems. Maybe you've heard of these before. They are considered to be the open, closed, and isolated systems. Out of curiosity, has anybody ever heard that terminology before, open, closed, or isolated systems? Maybe? Okay, let's do a quick recap here. Most of you are kind of, not sure. Let me describe an open system for you using both the picture and a different analogy. Here's a beaker or a test tube, and it's considered open. I think most of you can see why it's different than closed. The difference is that there is a cap on the top of the closed system. A different analogy would be our classroom right now. The door to the classroom is open, so it's an open system. If I were to close the classroom door, it would be a closed system. Okay, what does that mean about physics? Quick recap. What makes something physics? It's about the study of matter and energy. Okay. An open system allows matter to come and go as it pleases. As the door is open right now, if someone were to walk by our classroom, a person could physically come into our classroom. Matter could enter or exit. Or at least it has the possibility of doing so. A closed system is where you put a lid on something. What are you preventing happening in a closed system? Matter could no longer leave or enter, right? So if I were to close the door and lock it, in theory, none of you can get out. You have to stay here for an hour, right? Anyways. Does that make sense? An isolated system is very, very challenging to make. An isolated system is where you try to maybe surround this like a thermos. You know how a thermos is supposed to be isolated? Or maybe we use the word insulated as a synonym. What is an insulation supposed to do to a system? Why do we put insulation in a house? Yeah, so it keeps it warm, right? Or in the summertime, maybe it keeps it cold. What do we mean in different words then? Insulation is to try to prevent heat or energy loss. That's the second half of physics. Okay? Open systems allow both energy and matter to come and go. Closed systems close off the matter from being able to come and go, but energy is still allowed to transfer. An isolated system, if we insulate this, we're trying to even prevent energy from leaving, most likely in the form of heat loss. Does that make sense? So my final analogy is, let's use our classroom again. Let's say we close the door. Let's say we seal the classroom up airtight, and let's say that these vents right here, let's close those off too. That way that cold air can't be pumped into the classroom. That means that whatever energy that's in the classroom is stuck with it. So if it's really hot out, it's going to stay really hot. We have no air conditioning to cool us down. Does that make sense, that kind of concept? Now, here's why that matters. What we're going to be talking about today is a physics principle called, as you can see, conservation of energy. So we're going to be wanting to discuss the idea of energy being conserved. And we've actually already discussed a conservation law already in this course, conservation of mass. Conservation of mass basically means that whatever mass you start with, you should ideally end with. Well, by that same principle, whatever energy we start with, we ideally should end with in a very similar sort of way that we learned about in chemistry. Okay? We're going to assume that most systems are probably isolated. And that being said, most things do, I'm going to use quotes here, usually things lose energy over time. We try to make the most energy efficient appliances and energy efficient devices that we can, but the truth is that most things are not overly efficient. Usually there is a loss of energy over time, usually due to heat. Heat is one of the things that we really can't control. Slowly over time, heat will make its way out through this insulation right here. So here's a term that I've already discussed with you. It's called mechanical energy. Mechanical energy is the energy of objects that are moving, right? And there's actually two things that really are what we consider mechanical energy. There's kinetic energy and potential energy. And if you watch the YouTube video over the weekend, and if you haven't, by the way, you still can and should. It's not due anytime soon, but you should watch that Topic 4 video. You hopefully learned about a new formula for kinetic energy that goes like this. This is the energy of something in motion. It's 1/2 mv squared. That's the formula for kinetic energy. However, an object may also be in the air and have potential. As an example, if I were just to basically throw that eraser across the room, it really had two forms of energy. It had kinetic because I threw it, and so therefore it has a mass and a velocity. But if it's in the air, it has further ability to continue moving due to what we call the gravitational potential energy, based on the formula mass times gravity times a change in height. And if it has a further height amount that it can fall, a further distance that it can fall, well, then it continues to speed up, right? Right now, this pen that I'm holding here, is it currently moving? Does it have the capacity to move if I let it go? Sure, yeah, right? And that's because it has a change in height possible. Now I'm going to put it on this table. Okay, now that it's not rolling anymore, does it have the capacity to really fall any further? Not unless the table collapses. Now, I mean, to be fair, everything, I guess, if you consider it that way, has the potential to keep falling. We could fall through the floor right now because we're on the second floor of Chinook High, right? I don't expect that to happen, but we technically have potential energy. We could fall. That being said, is there likely to be a change in height of the object as it sits on the table? Probably not. But if I lift it up in the air, well, now there's a change in height and it can fall. If this object falls a foot versus if this object falls 4 feet, doesn't that change how much potential it has? Right? And hopefully you recognize the further that things fall, the faster they're going to eventually go. Okay? Well, here's the theory. According to the law of conservation of energy, in theory, the amount of energy should remain constant, kind of simple. And it's not before and after. Start with should equal the amount of energy you get. And from hang out with so you can kind of build yourself your own formula like this. Whatever potential you start with, and whatever kinetic you start with, all of those equal whatever. Let's say there's a falling rock. The falling rock has potential energy at the top of its plate. Time it's going to change that energy into kinetic energy as the rock. One way of looking at it is that potential energy will go down, and if the potential energy goes down, kinetic energy. Well, now they have potential mass, gravity, and their possible speed, and their possible speed and height. However far they roll down the hill, they can repeat kinetic energy. So imagine at the top of the hill, they're no longer cycling with their feet, they're coasting, and the cyclist starts going downhill. Well, then this potential energy will start to turn back into kinetic energy. And there's watches it. bar graph here to keep track of this. We have a snowboarder at the top of the bar graph. Well, if the bar graph goes down, lose energy. What happened? The kinetic energy went up. We'll have to wait until the animation plays. Let's talk about it again here. So, almost at the end here. Potential energy is really high, right? So the potential energy bar graph is really high. As potential goes down, kinetic goes up. Because what's happening is gaining speed. Now, the total mechanical energy, which is this green bar graph, really is. What's cool about this graph here is that slowly over time, as this person hits the unpacked snow, they're eventually slowing down. And you can see that this bar graph right here, W, went to 50. Anyone have any idea what W is? Work. Good try. Work. And if you guys remember our talk on Friday, work is anything that causes you to change your energy. And so once this person right here is slowing down, see their kinetic energy is dropping? Well, it's because negative work was being done to slow them down. Well, think of it. Ideally, what should happen is that potential energy goes down and it goes up. As your downhill speed. Another one. This bar graph is the total mechanical energy. How much energy there is. And really, it's fluctuating between. Where will this particular roller coaster cart be going fast? Probably at the bottom. Right? See how the speed is picking back up here and then it slows down a little bit and then picks up speed, right? Just think of it from the top here. Going slow, then he's going to go faster, 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 faster. Right here, he went the fastest. But then when you go back uphill, you're kind of lose a little bit of speed and then go faster again. And then you're going to lose a little bit of speed and then go faster. And you can see that in these fluctuating graphs here is that as your kinetic energy goes down, it's because you gain potential due to increasing your height. Okay. A couple more. Here is a cannonball being shot into the air. And it more or less has the same concept going on here, is that as one goes up, the other goes down. So as this thing gets higher and higher up into the air, it actually loses some speed. It has a lot of speed right out of the cannon, right? And then as it goes up in the air, the potential energy due to gravity goes up, and then it comes back down again. See how the kinetic energy is really high as the red bar graph? As soon as the cannonball is going to hit the ground right here, that's when it'll be going the fastest. The main goal, though, is that your total mechanical energy was constant the whole way through. Ideally, no energy is lost over time. Okay. So, quick summary before we do some of the math here then. The theory I want you to understand then is that your mechanical energy is really the sum of your kinetic and potential. You have the potential more, and you're also in add those two energies together, it's mechanical. Kinetic energy, in case you're not familiar with this formula yet, is 1/2 mv². Potential energy is mass times gravity, times however high you are. Occasionally, we'll account for a theory. We don't do that here, but we can because there are other formulas. Let's try some more math. You can have a sheet of paper with something to write on. You may want to follow along and write down some notes. Rarely do I kind of suggest, hey, you need to take notes, but this would be one of those few times where I'm not going to make it for you to, but I would strongly suggest that it would be worth your while to try this along with me, because this is one of the more challenging. We have to go through that 4-step process before we can solve this. Right? You just stopped by. Hi. Okay, so here's our goal on some of these math questions. Step 1, we have to identify what formula to use, or, as we're going to do today, we have to build ourselves our own formula. And that's found. Step 2, we're going to work on our algebra skills. Like I said, for those of you who are really strong in algebra and who like algebra and math, you're probably going to like this. For those of you who aren't, practice. Step 3 then, we're going to set variables. Step 4, then we work on adding. so that you kind of have how long for. Sure. Let's give an example. Let's say there's a heavy object with mass of 50 kilograms, and it's dropped from a vertical distance of 12 meters above the ground. The question is, what is the speed of the object? Let me walk you through some thought processes. You may start looking at all these formulas on the board, and you want to start walking through and saying, hey, can I solve with any of these formulas? So I'm going to start writing them all out again. There's D equals V and T. What ultimately is the question asking for? Well, it's asking for the speed of the object as it hits the ground, right? So speed is V for velocity. Okay, so if I wanted to try to use this formula here, I would need to know D over T. I know D, because that's a distance, but do I know time? Okay, so that formula's out. Let's try another one. We'll go through all of them, by the way. D, V, A, and T. As I go through this one right here, this is another possible formula. We might want to solve for this velocity right here. Do I know acceleration and time? Actually, we do know acceleration, by the way. Does anyone remember what the acceleration due to gravity number was that we talked about last week Friday? Yeah, it's 9.81. So we actually do know the acceleration due to gravity on Earth. It's always 9.81 meters per second squared. That being said, though, do we know time? We still don't know time. Okay, so this formula is out, right? I'm going to go through the process of this once, by the way. I won't do this every example. Another formula we've learned is work is equal to force times distance. That's not even remotely helpful because we need velocity, and there's no velocity in this, so that one's out. Fg over mg, there's another formula. That one's out. Anyways, do you guys kind of get how you could start walking through all the formulas that you learned one at a time? And what you may end up coming across is a scenario where you're like, Chris, I don't have a single formula that I can really use because none of them really fit. And sometimes you have to do this last one here, build your own formula. And Science 10 students, this is not just something you're going to be frustrated with. My Physics 30 students, they find this the most challenging part as well, is where do you start? You have to start, in this case here, with the concept of conservation of energy. I'm just going to draw a picture here. Here's an object that is, like, say, on the edge of a cliff, 12.0 meters above the ground. So 12 meters above the ground. And this object right here, whatever it is about to fall. What sort of energy does this object have when it's up high in the air? It has potential, yeah. Okay, so in my before scenario, we know that we have potential due to gravity. Now, does it have kinetic energy if it's being dropped? But like before I let go of it, the instant before I let go of it, imagine again, as we're going to do in this lab on Wednesday and Thursday, that you were to look at like the frame by frame video of me dropping something. If I just let it go, does it have a speed before I let it go? I'd say no. If I were to throw it, that's different. But if I just let it go, it wasn't moving until gravity took over and started moving it. So I would say that there's no kinetic energy. At this particular moment right here, there's gravitational potential energy. But if we were considering whether there's kinetic energy, I'd say, well, no, there's not. Because I didn't throw it, I just dropped it. So that's my before scenario. Then the ball goes through the air. And we want to consider this to be an isolated system. Isolated system meaning that no energy is lost. Okay? So it would be like if we could close the door and vent up the vents so that no energy gets in or out. Or it's like having a thermos where no heat escapes. Chances are there will be at least some energy loss due to like friction and wind resistance, but we like to pretend there isn't any loss along the way. So let's then consider the ball the instant before it hits the ground. I'm not talking about it when it has hit the ground and is sitting there. For example, here's the same scenario again. I'm dropping a pen. Okay, the pen is now sitting on the ground resting there. You might say, Chris, there's no potential because it's on the ground, and there's no kinetic energy because it's not moving. I want to talk about that millisecond before the ball or pen or whatever the object is hits the ground. What's going on there? Well, I would say it has kinetic energy because it was moving that fraction before it hits the ground. But does it have potential to move any further? And I'd say, well, no, because it's basically right on the ground. It's about to crash. But we're talking the millisecond before the crash. And so here's how we're going to build ourselves a formula. Ideally, what should happen is all of the potential energy that we started with up here should turn into kinetic energy the millisecond before it hits the ground. Here's why we care then. Remember how I was looking through all these formulas on the board here and going, none of them really fit? Well, now we're going to make our own formula. The formula for potential energy is mass times gravity times a change in height. And the formula for kinetic energy is 1/2 of mass times velocity squared. What was that? And I lost you up on this one here. Okay, so one of the things that we'll have to practice then is knowing these formulas is that the formula for gravitational energy is mg delta h, and the formula for kinetic is 1/2 mv squared. So all I'm doing is I'm just taking this formula right here that's written on the board there, and I'm replacing it with this, and I'm taking this formula right here, and I'm replacing it with those variables there. So we will have to work on those formulas. Rearrange this for the variable we're looking at. We were trying to solve for velocity, so we want to try to solve for velocity. Well, one of the things we can do is start plugging in some numbers. I'm just going to draw an arrow. Do we know the mass of the object? Go back up in the question. Do we know mass? Yeah, 50 kilograms. Okay, so let's write that in. 50. Okay. Do we know what G is? What was G again? Gravity, yeah. How fast does gravity accelerate things on Earth? 9.81. Okay, so I'll plug that in for G. So this is what we call the substitute. Mass is gravity. And do we know how far this thing was going to fall? Yeah, 12 meters, because it's what it said. It said it was going to fall 12 meters. Okay. So what I'm doing is I'm substituting in some variables. Mass is 50. Gravity is always 981, and height is 12. And then if I go over here to the second half of my built equation, it's 1/2 of mass. It's an isolated. It is the mass the same as it was at the start of class 1 because kids walked in, right? Because the door is open, right? But if we have what's ideally a closed or isolated system, the mass shouldn't change from before to afterwards, so mass should still be 50. And then the last thing we need to do is we're trying to solve for velocity. So I'm going to leave that as v squared. And what's happened now is I've basically substituted in all of the different values. One left than I was. And again, this is where some of you are going to be like, oh, I hate this. And some of you are going to be like, this, I don't have to. Well, we have to algebraically now solve for v. I know. Step 1. How do we get rid of a 1/2 on one side of the equation? Multiply by 2. That's fantastic. Yeah, because if you were to times, say, this side right here by 2, 1/2 and times 2, they just multiply one side by both sides by 2. So I'll do a times 2 over here. And I'm going to try to color this to kind of keep things straight. So I've now found a way to get rid of the 1/2. We now need to get rid of the times by 50. So if you want to get rid of the times by 50, okay, so I divide both sides by 50. So letting green here, divide both sides by 50. And then the last step of our algebra, we then need to get rid of the fact that it's these. Squaring is square rooting. So if I were to square root this side of the equation here and square root the entirety of that side here, it's squared. What with speed. So I'm going to try to write this a little bit nicer here. It's going to be equal to the square root of 2 times 50 times 9.81. Times 12.0, all divided by 50 again. Now, one thing that some of you may notice is, hang on, there's a 50 right here, there's a 50 right there. Did we catch that there? There's a 50 here and there's a 50 here. What happens when you have 50 divided by 50? Yeah, in theory, they could cancel out, so I could even simplify this a little bit. All we need to type into our calculators then is 2 times 9.81 times 12 and square root it. And we'll get a velocity. So I'm going to try that, then I'm going to walk you through the process again, and we're going to do a few examples. So please don't feel like you have to understand this after one example. or even after 4 examples. Okay? We're just going to keep practicing these skills. So anyways, if you have a calculator, 2 times 9.81 times 12, and if you square root the whole thing, I get an answer of this. I'll write out most of the digits. I got 15.34405. Okay, 2 more thoughts. We now have to do the last thing to make this physics again. We need significant digits, and we need some appropriate units. Let's start with units. What is velocity measured in? Meters per second. Yeah, that's the official way we try to measure things in physics. Meters per second. Second thing is we got to figure out how many digits do we keep. Do we keep the? I mean, we got to keep at least the 1 probably, right? But like, do we have to round this up to 20? Do we have to round it to 15, 15.3? So the key then is to look back at what we used. We used 50.0, that has 3 digits. We used 12.0, that has 3 digits. So based on that, we better keep 3 digits. So going back down to the bottom here, 3 digits. 1 gets kept, 5 gets kept. 3 is it more than half? Is this 4 right here more than halfway for rounding? No. Okay, so the best answer is 15.3. Okay, so let's walk through some of the steps that we did there. Because for some of you, like I said, you may be going, Chris, I got this. And some of you, your head may be spinning, and that's fine, okay? Be patient. I'll work with anybody. Step 1 was we had to first identify how do we even build a formula, and that is a hard step. What we recognized is that there was only gravitational energy as we were dropping it, and then as it hit the ground, the instant it hit the ground, all there was kinetic. We made them equal to each other, assuming no loss of energy over time. So what we start with finishes what we finish with after. We then replaced formulas using algebra by saying, well, the formula for gravitational energy is mgh. The formula for kinetic energy is 1/2 mv squared. That's what the next step was. The more you get used to these formulas, the easier to substitute. The next step after that was I started plugging in some values. Mass was 50, gravity was 981, height was 12. Mass over here under the mess is 50, and v stayed as v because we didn't know what the velocity was. We then used our algebra skills to get rid of the 1/2, the 50, and the square rooting bit, and then we solved. Let me try another one. By the way, don't forget, I'm recording this video, so if your head is spinning and you're lost, you can rewatch this, okay? But let's try some more examples. I have 4. Another scenario. Let's say there's a child playing with a toy at the top of a balcony of a theater. So like, the kid got brought along to the opera. I don't know why this balcony is 19.2 meters above the ground, because that's ridiculously high. But anyways, the child... Okay. This is honestly the exact same scenario. Okay. Here is the balcony up top here. Here's the little kid with their stuffy. So a little stuffy up there. What sort of energy does the stuffy have if it's dropped? Just potential due to gravity. That's it. Then the stuffy, whatever it is, will fall down to the ground and it will hit the ground. And the instant before it hits the ground, all it will have is kinetic. What we're really looking at in this scenario is something similar to this animation I had earlier. Let me just show you one here again. As the skier is going down the hill, consider it as it starts here. At the top, all it has is potential energy. And then as the potential energy drops, the kinetic energy goes up. And we want to figure out what happens at this point right here, right when it hits the bottom, when all of the potential's gone, and all you have left is kinetic. So let's build ourselves that formula again. We'll do that step. Sometimes it helps to think of a before energy, before and after. What energy did it have before? Potential. What energy did it have afterwards? Kinetic. Okay. So once you get more familiar with change in height. Building ourselves a formula. the potential energy here will turn into kinetic energy here. As one goes down, the other kind of goes up. Now, the last time I tried this, what I did is I plugged in numbers for algebra. Let's actually do math rearrangement. Because these are the same steps. What did we do the last time around? Theory back in the 1700s that mass didn't affect gravity. You dropped Cannonball 1 and Cannonball 2, they fell at the same speed. And that's actually what this has now helped us to prove, is that it really doesn't matter what the mass of the object was. I know I told you that it was 120 grams. That's irrelevant, because actually this mass number over here cancels on that side. It doesn't matter whether the mass was going to be 100 or 50 or 20. If I plugged those numbers in right there, they'd cancel. Okay. There's one more thing I need to do. I need to get rid of this squared sign right here. And so to do the opposite, square root both sides. Cool. So here's my new formula. The square root of 2 times g times delta 2. Now, that is probably the single hardest thing that most kids struggle with in physics, is 1, building your formula, 2, being able to do the algebra. Okay, I'll say this a million times today. This is not all of physics. This is a fairly high level here. If you're looking at this going, Chris, I'm not going to be great at this, that's fine. Okay, there'll be 1 or 2 questions on this. I will help you with them as you need to. Right? If you're looking at this going, yeah, I can follow along with this, okay, then yeah, maybe physics is a class you'd like to continue with. Not everyone is going to be a physicist. That's fine. That's cool. Okay. Anyways, this is for velocity. Here's the next step then. Now let's substitute in our variables. So we're going to take 2. We're going to times by gravity, which is always on Earth, 9.81. And we'll times by a change in height value. How far did this thing fall? 19.2 meters. And that'll give us the velocity. So take your calculator and try this. 2 times 9.81 times by 19.2. And if you square root that whole value, I got this. I got a velocity of 19.40886, etc. Okay, let's talk about those 4 steps that are on the board there. Step 1, identify and build the formula. Step 2, use your algebra skills to rearrange it. Step 3, substitute. We're now up to step 4. We need to add significant digits and some zeros. So going back up to the top, of the values we use, look at the number. Hang on. Something that you would actually measure. This isn't a measured number. 9.81 wasn't really that. Meters per second. So that's a really great question. The mass, if the mass had been 2 digits, we'd still count with 3 because mass was not used in our calculations. As a similar example, I might say that it was 4 degrees outside today. That has 1 sig dig. Did I use the 4 degrees though? Not right? Like, okay. And if I were to say that it happened to take 5 seconds, and that was 1 sig dig, but did we use 5 seconds in the calculations? So we only, to hopefully answer your question here, we only really care about significant digits based on variables that are measured, that are used. So because this mass up here of 120 grams maybe has 2 sig, we never used it. It wasn't relevant, so we don't have to worry about it. Yeah, we didn't need to. Yeah. Do you see how that 50 right here, it canceled in the previous question? So like we could have just skipped it the entire time. We didn't need to worry about what that mass was. Okay. Let's try another example. Okay. This is one of those things where it's frustrating. It's like when this is why I rarely give worksheets, honestly, because for some people you're probably like, okay, I got it, and for some of you are like, Chris, I got lost 10 minutes ago, and I'm starting to mentally check out. Okay. I need to ask you, do your best to stay with me. I get it. Sometimes when you're like, man, I got lost. Right? Repetition. Let's try this one here. There's a heavy object with a mass of 26 kilograms. It was thrown vertically down. Some visuals. In our previous examples, now throwing it. Starts the exact same way. There's a person top of it, and there's an object. Oh, wait. Let's get to the that the object has. Stay with me, okay? I've got 2 more examples left, okay? First of all, the object has gravitational energy because it's up high in the air. It has the potential to fall. However, because this person also threw it, there's also kinetic energy. Now, as the object then goes on its merry way and slowly but surely falls and hits the ground, if you imagine that bar graph of gravitational energy versus kinetic energy, the gravitational energy bar graph will be going down as the kinetic energy bar graph goes up, because this thing will speed up over time. The instant before this object hits the ground, all that will be left will be kinetic energy, because the gravitational energy bar will be down to nothing and the kinetic energy bar will be up to full. So that gets our scenario started. What's different about this one then is how we build our formula. Last time around, it looked like this. Our gravitational energy turned into kinetic energy. But this time, because we threw the object, it had some kinetic energy to begin with as well. So we have gravitational energy and kinetic energy to start with, and then just kinetic energy to end with. That's the twist. And this is what makes physics sometimes very challenging for students, is that you have to kind of build yourself your own formula by understanding what energy we started with and finished with just to get to the building stage. And that's just step 1. Now let's try step 2. Let's now start to use our algebra skills to manipulate these formulas. What is the formula for EG? Mass times gravity times a change in height. We're going to use colors to help code this. What's the formula for kinetic energy? 1/2 mv squared. And for the final one, what's the formula for kinetic energy? Well, it's still 1/2 mv squared. However, I'm putting them in different colors to make a point here. In purple, purple is the velocity of the ball when we throw it at the top up here. So if I can color coordinate that, where's purple again? This is the velocity of the ball right here. But in green, down here at the bottom, eventually the ball will hit the ground. We want the velocity down here. So we actually have 2 different velocities. We have the starting velocity of what we throw it, and then the final velocity as it hits the ground. So that's why I'm color coding it. Of these 2 velocities here, which one do we need to solve for? The speed when it reaches the ground? We need to solve for the velocity right here. Okay, let's figure out how to algebra this. This is, like I said, this is one of the single hardest things we will do. If you're still lost and struggling, I don't have an expectation that you're supposed to be fantastic at this, right away. We'll practice it. these items over here on this side right here, I'm going to put a big bracket around them just to kind of keep them separated. Last time around, how did we get rid of a 1/2? Times by 2, okay. So I'm just going to get rid of this, and I'm going to times everything here by 2. And maybe you can see why I need this bracket right now, because everything needs to be times by 2. Which means if you know your distribution property in physics, it means that what you're really doing is 2mg delta h. And when you times the 1/2 mv squared by 2 there, the 1/2 and the 2 kind of cancel, and it just leaves you with mv squared. Can I say that one more time? We times this side right here by 2 to cancel the 1/2. But it means that everything on this side gets times by 2. So when the mgh gets times by 2, you have 2 mgh's. But when you take this 2 and times it by 1/2 mv squared, that also cancels out the 1/2. Okay, so that's step 1. Step 2, we have to get rid of the mass over here, so we're going to divide by mass. Well, all of this stuff over here had to get divided by mass, which means that both of these two individual terms get divided by mass. This term gets divided by mass, and this term gets divided by mass. And that isolates. Now here's something really cool though. Has the mass changed? The mass of whatever the object right here is, did it change as it fell? Not in an isolated system. So that means that you can actually cancel this mass with this one right here, this mass with this one right here, and we're almost there. The last step is that this was equal to v squared. So to undo the squaring of something, you've got to square root everything. So you need to square root all of this. It's getting a little bit messy here in terms of what's left, but hopefully you're kind of able to follow what's there. What I'm left with is a 2g delta h plus v squared, and all of that got square rooted to give me v. And again, this is where some students like, wow, math, eh? Yeah.
How can we have v on one side and
V on the other side? Okay, so why don't I color code them again, right? Because there's a v, that's the initial velocity, and then there's the v, that's the final velocity. So why don't I color code them again here? This v right here was the velocity as we threw the ball down, and this velocity right here is the velocity of the ball as it's about to hit the ground. Tori. Because it was squared right here, but I then square rooted both sides, and so that's why there's a square root over here to take that's place. So what we used to have was a v squared equals some stuff over here. And what we did is we square rooted this side, and we square rooted this side, and then when you square a square root, does that make sense how it gets rid of it? Oh, great question. Okay. It does. Okay. Tori asked a really great question. I think what you might be thinking is, can we write it like this? Square root of 2g delta h plus v, because you're looking at this going, hey, doesn't v squared and square root, don't those cancel? Is that kind of what you're getting at here?
Well, if you write it as square root plus v squared and then square root altogether, then can you rewrite it as, or can you rewrite it as 2g delta h plus v?
Yep. But we still need to have the square root on top of all of it though, right? So let's clean this up a little bit because it's starting to get a little messy. Let me back up here. Let's go back to, here. Okay. Okay, so why don't I take it back from here again, and now I'll ask your question again. Can I redo the first two steps though? So first, let's times both sides by 2. So if I times this side by 2, this goes away. If I times that by 2, and that makes that one go away. Is that okay there? Tori, you're the one who asked the question, so I'm going to look at you. Is that okay with how it got? Then I'm this one and cancels this one. Just over there. Okay, so we can totally do that. Let's just undo the work here. Okay, so one more time. So let's times this by 2, times this by 2, times this by 2, and that goes away. And then what you want to do is you want it to divide by mass? Okay, so I'll divide by mass, I'll divide this one by mass, and I'll divide this one by mass, and that makes that cancel. Can everyone who's having a bit of a side conversation, please stop that? I get this is a really hard and frustrating lesson. That's not an excuse just to quit. Okay. I get that it's challenging, but when people have questions, I'd really love it if everybody could still give me the best attention you can. I promise there's only one more example left after this. And we will work on this over the next couple of days. But this is a necessity. I got to try to explain to everybody. Okay, so now your question. We want to take care of the squared sign, right? Okay, so can you ask your question one more time now from this point here? Okay. So here's one thing that we can't do, though. We can't square root this, and square root this. Okay? Because that's not how square roots work. I may need to go into a deeper lesson as to why it's not valid to do that. But what we have to do is we have to square root an entire side. Okay? So hopefully we're in agreement, though, that this velocity right here, we need to get rid of that squared sign, right? Okay, so I'm going to square root this right here. Okay? It means that I'll be left with just velocity. We have to square root this entire side right here, which means the entire piece of this has to get square rooted. And one of the reasons why that matters is that if I were to give you, for example, 3 equals 1 plus 2, okay? Would you agree that that's a true statement? 3 is 1 plus 2? Okay. If I were to square root this side and square root all of these independently, I challenge you, try that in your calculator. The square root of 3 is actually not equal to the square root of 1 plus the square root of 2. Unfortunately, square roots don't work like that, where you can just put a square root on each term. But what you can do is square root both sides like this. That is considered to be valid in math, but you can't actually square root them all individually. Okay. So I hope that somewhat answered your question, because here's the part that, I mean, a lot of you are, I get it. Some of you are like really lost on this step. I don't expect that when I deliver a mass lesson to all of you that everyone is supposed to pick this up. That's okay. But this would be the formula we're going to finish with. Okay. Harrison. You absolutely could. Yeah, you could make this C be velocity 1 and velocity 2. Okay, that'll work. You can. Okay, let's try finishing this off, and we'll try another example, because sometimes it doesn't help to dwell on a question too long. Okay, I feel like we're dwelling on this one too long. We'll try other ones. Go ahead, ask a question, though. Yeah. It's okay. Because we're not able to basically square root this one and square root this one. Yeah, that's why. So it has to remain slightly different. Okay, let's give this one a try, and then maybe I'll try to work on targeted questions. Our final answer will be 2 times 9.81. Okay, now I've lost track here. How high did this thing fall from? Oh, here it is. Okay, this number right here, 1.00 times 10 to the 2. What is that number? 1.00 times 10 to the 2. What is that? Yeah, it's actually number 100. Okay. And then we will add v, the initial speed squared, and I think the initial speed was 10. Okay. Most students are probably okay with typing this into their calculator and getting the right answer. That's not usually the hardest part. It's usually getting to there. That causes you to get lost. Okay. So anyways, we'll get an answer. We'll try another example, and then we're going to work on this over the next couple of days. So please, don't stress that you're not picking up on this immediately. I got a velocity when I was done of 45.409, etc. is what v was equal to. Based on the significant digits, this had 3, I used that number. This had 3, I used that number. This had 3, I didn't even use that number. So it looks like I get 3. So let's make this be 45.4 meters per second. Whew. That's it. Okay. Let's try one more example. And then we need to stop, because this is something that we'll discover is if you're in the spiral of this is frustrating, you don't get it, doing 10 more won't help, right? So I do want to just try one more example here. The goal is we're going to refresh. We'll start again fresh tomorrow. We're going to do a lab on this on Thursday and Wednesday. We'll work on this next week. So I've said this before. I apologize if I or any other teacher has made you feel like I'm supposed to learn this on Monday and you're supposed to be able to do it for the test on Tuesday. This is one of the most challenging things that we'll work on. So please try not to get so frustrated or stressed out that you're like, I'm getting lost on steps. That's okay. That's normal, in fact. Last example. A kid shoots a Nerf gun from the top floor of his house at his sister and her friends. The gun has the ability to shoot a foam dart of 12 grams at 3.6 meters per second. And this one says when the foam dart hits the sister, it's traveling 8.2 meters per second. How high was the dart shot from? So let's see what we can do on this last one here, and then we're going to call it quits for the class, because at some point, doing more questions doesn't help. So I think the way this worked is that the kid has his toy Nerf gun, and he's shooting the toy Nerf gun. And so really, there's two things happening. The gun itself is shooting with a velocity. And because he's shooting from the top of the house at his sister and her friends down here, really as this thing is being shot, let's consider the energies. Up here, well, the gun shot with some speed, right? There's kinetic energy. And because even if this person just dropped the dart, there'd have been potential energy. Well, let's say the dart then comes all the way down here and hits the sister and the friends down here. Well, all that should be left at that point is just kinetic energy. Because what should have happened is as the gravitational goes down, the kinetic goes up. And we can actually see that in the numbers we were given. The dart started at 3.6 meters per second, and it accelerated up to 8.2 because as potential went down, kinetic went up. Now, this is our fourth crack at this. Hopefully you're starting to see some patterns. Okay. Again, don't stress if we're not there yet. But let's write out what we have before and after for energy. Before we started, the gun was shot with some kinetic energy, and the dart was above the ground. We have potential. And then after the gun has finally shot the bullet, the dart, and it's flown through the air, eventually all that will be left is some kinetic energy when the dart hits the sister and her friends. That's step one. Okay, step two. I'll color coordinate this again. What's the formula for kinetic energy? 1/2 mv squared. What's the formula for potential energy? Mass times the gravity times a change in height. And then, again, this comes back to, well, why do you do this twice? Well, the reason we need to do it twice is because there is an initial velocity and there's a final velocity. Okay, most students are usually okay up to this point here. And then this is the point where, like I said, this is where math skills are so challenging. We need to figure out what we're solving for. What are we asked to solve for in this question? How high the dart was shot from. So this is probably the single most challenging step, is we need to try to find a way to isolate this equation for the height that this was shot from. How do we isolate for that height value right there? Okay. Step one. We actually have to work backwards from bed mass. We have to get rid of this g for gravity, this m for mass right here, and we have to get rid of this entire term over here. This 1/2 mv squared also has to be moved. So I'm going to start with that. This entire term right here, all multiplied together, needs to get moved to the other side of the equation. It's kind of like if you're given the math equation 3 plus x equals 4. This over here is the 3, and we need to minus 3 on both sides just to get that moved over. Okay. Then there's still mass and gravity we need to get rid of as well. That's like if there was like a 2 in front of this. Eventually you'll have to divide both sides by 2. So in terms of your algebra steps, first we're going to minus 1/2 mv squared from both sides of the equation. Now, what this tends to let kids think is that, hang on a sec here, if I have 1/2 mv squared and I minus 1/2 mv squared, wouldn't that mean that there's nothing left? But hang on. Are these two velocities right here the same velocities as each other? No. And that, Harrison, you had a great idea earlier. Maybe we should call this one here velocity 2 and this one velocity 1, just to kind of keep them straight because there's two different speeds. Okay. Next step, we still have to get h by itself by isolating and getting rid of mass and gravity. Now, if you want to divide both sides by mass, that'll work. So divide this side by mass. If you divide each of these terms here by mass, you can actually cancel mass out entirely. And so it'll leave you with this, gravity times a change in height equals 1/2 of v2 squared minus 1/2 of v1 squared. And then our last step is we need to divide both of these things by gravity. And if we divide all of these by gravity, we'll finally have built ourselves a formula for height. Yeah, you could just divide by mg. I just did them in steps. You're right, though, Tori. You could have divided by mg just at the same time. When you're done, you should get a formula that looks something like this. 1/2 of v2 squared minus 1/2 of v1 squared, all divided by g, or in sections. Either one works. There's your formula for the change in height. Here's what I need from you guys. I need for you to be able to identify for me where you get stuck, because the help that I give you depends on where you get lost. If you got lost with me making the formula, I have different strategies than if you got lost during the algebra stage. Okay? Here's an entirely different stage. If it's okay, if you got completely lost in the last four seconds of writing out all this gibberish here, if you don't get that, I need you to restart here again, though. Say I give you this formula. Are you okay at this stage here plugging in numbers? Let's talk about that part then. This is the substitution part. Okay. I know you may have got lost up to here, but can you plug in numbers? Can you take 1/2 of v2? Okay, what was v2 again? Second velocity was 8.2 meters per second. 1/2 of v1, what was the initial velocity? It was, what is that, 3.6? And then g here for gravity is 9.81. What I need is some honest reflection from you and letting me know, even though you might not have known how to make this formula right here, are you able to plug numbers into the formula though? Okay, we'll do that last step then. So we're going to do 1/2 of 8.2 squared minus 1/2 of 3.6 squared. And when I'm done, I'm going to divide it all by 9.81. The final answer that I got was 2.8 meters. Okay. If you can do the last step, that's fine too. Because here's the good news. We have a degraded classroom. I'm not going to be testing you in the traditional sense on this. But I do want to understand whether you can do all the little bits and pieces along the way. Okay? And I get that there's a big part of physics that requires background skills that not everybody comes in with the same ability at. And that's okay. I can live with that. So can I give one last thought here and then I'll be quiet? Okay. Here's what I need you guys to help me with. Those 4 steps on the sidewall. We're going to work on this tomorrow with a worksheet. We're going to do a lab on this on Wednesday and Thursday. Are you okay with identifying which formula you need and building it? That's a step. Step 2, the one that catches most kids. Do you have the algebra skills needed to manipulate it? Step 3, can you substitute variables? Step 4, can you do units and sig digs? On a traditional test, if you can't do all of the steps, you'd get it wrong. In my class, if all you're struggling with is the algebra stuff, I'll help you with the algebra if you can do the rest of it. Does that make sense? If that's the only thing that's getting you stuck is the background math skills, I will do that part for you on your performance task if you need. As long as you can identify the right formula, as long as you can plug in the right numbers, I'll help with that part. Thank you guys for staying with me for a very long lesson, because that was an hour, like I think I promised. It's a long time to listen. Okay. Sometimes it gets overwhelming. Here's what I want you guys to do then. On Moodle, like we always do at the end of a lesson, I've got 5 practice questions. You'll actually notice that only 2 of them even involve math calculations. The other ones just ask about, do you understand the concept? I'd like you to try those, but this is something I need done for tomorrow, okay? I don't assign homework, because honestly, there's no consequence, but I need you to do this for my help. Here are the 3 questions I'm going to ask you to do on the reflection. Please do them sometime today. Of the things I taught you today, one was the different types of systems. This has just as much value as doing the math equations. It does. Just because you can't do one math question doesn't mean you fail and you're horrible at this. If you understand the types of systems, that's important. Okay. Number 2, do you understand the idea about how isolated systems conserve energy, about how if this one goes down, this one goes up? Okay. And then for this last one right here, I need some honest feedback so I can help you tomorrow. Do you know how to create your own formulas depending on how to use conservation of energy principles? I didn't actually ask about where your algebra skills are. Okay, that's not my focus. All I want to know is, do you feel like you understood in this example right here where I came up with, yeah, of course, where I came up with this concept here of kinetic and gravitational equaling kinetic. If you feel like you can understand that, that's the physics part. Okay? Okay, so anyways, please work on that reflection. You have about 5 minutes left here. Okay? Let me know where you're at. And then tomorrow we're going to do something we rarely do. We're going to work on a worksheet. Okay? And I will come out and I will help people at different stages of where you're at in terms of this concept. Okay? Okay, thanks everybody for sticking with this long lesson. I appreciate it. That was an hour exactly.